Swayam Prabha. Digital India. Educated India.
Welcome back on this series of lectures on muffler acoustics. We stopped at the momentum equation in the last lecture 3. So, in this lecture our goal will be to linearize the momentum continuity and momentum equation appropriately by dropping certain higher order terms and then combining that with your equation of state, which is basically your isentropic equation, to finally arrive at the one dimensional wave equation. So, let us first write down the continuity equation what I basically briefly mentioned. This was your continuity equation that I mentioned. Let me encircle it again here. So, del T of rho, where rho here is the total density, similarly use the velocity. Often in flow ducts we have a mean velocity also and small perturbation velocity. So, here of course, we will just consider right now we will just consider u as the particle velocity. We will consider a stationary medium, that is look in mufflers of used in automotive application in exhaust system of automobiles, there is usually a flow. So, it is something like there is a constant flow plus there are disturbances that are convected in along the direction of the flow. So, right now for the development of these equations, the basic wave equation without flow, we are just going to ignore the mean flow effect and just consider u as the acoustic particle velocity. And pressure of course is the ambient pressure plus the pressure perturbations. So, now let us consider this continuity equation what I have encircled and go about the process of linearization. Before we begin the linearization process, the following things might be important, that rho naught T is 0, that is there is no temporal change in the ambient density. It is important because we eventually would want to do something about this term density times this. So, this can be decomposed as ambient density times this density, and this is this thing. Similarly, now when we pull out the continuity equation which is somewhere here and start expanding the terms, there is also another thing that I want to point out is that we are also considering that spatially the ambient density is not changing. That is to say, we do not have a stratified medium, or well, we are not considering those cases. We are just considering a medium in which the ambient density of air or any gas does not change. It is a uniform density gas with respect to space. Now, with this, when we pull out the continuity equation and use these relations, what we eventually get is something like rho T plus u times Px plus rho naught times ux plus this is 0. So, now let us underline and identify terms which are first order and which are sort of second order. Now, that is the process of linearization. So, we immediately recognize that intuition says that rho tilde with respect to t, that is the first order term, and so is this term, whereas these two terms are second order. The reasons can be justified by noting that, well, rho tilde is much smaller than the ambient density, and your velocity is much smaller than the sound speed, or in other words, P tilde is divided by rho naught is much less than 1. Now, there might be a concern that if rho tilde is small, its temporal derivative might not be small. Similarly, if u is small, its spatial derivative ux need not be small. It is a well justified concern, and that can be elevated by considering the a more physical argument, when in the beginning lectures we talked about the disturbances propagating at sound speed c naught. So, if we consider the disturbance delta rho or simply rho tilde, if this propagates, if you take a temporal derivative of this, so this is your rho t approximately, since its acoustic disturbance is small speed, for small speed equations this would approximately be equal to c naught times rho naught times x. Okay. So, basically what it means is that if we were to basically substitute this relation in the above equation, let us see what we get. So, here we substitute c naught times rho tilde x plus u times rho x plus rho naught times ux plus rho x times ux is equal to 0. So, this is an important substitution that we made, and let us compare the terms. So, clearly if we take well, this term and this term rho tilde x, rho tilde suffix x, that is derivative with respect to x. So, this term if we take common, and c naught and u, and we also made an assumption that u naught is much smaller than c naught. So, clearly this is the dominant term, and this term sort of can be ignored. And similarly in these two terms, if we take ux common and you have rho naught plus rho tilde, so we will see clearly that this term is a smaller order term, and only this term would survive. So, basically what it means is that if you pull out this equation, only this particular term would survive, rho tilde t and rho naught times ux, which is so this is what we are going to get. Another way of looking at this linearization process for the continuity equation is basically to non-dimensionalize the variable. So, suppose if we introduce variable called delta rho dagger is p rho tilde divided by rho naught, and your u dagger is u times c naught, and some time is nothing but t by tc, where tc, the choice tc can be arbitrary, and z is equal to x divided by c naught t. With this non-dimensionalization choice, what we end up, we can put this continuity equation given in here in the following form: delta rho tau dagger plus u dagger delta rho dagger plus u dagger z plus delta rho dagger u z dagger is equal to 0. So, now as we have already assumed that this quantity has to be much smaller, because rho tilde by rho naught is much smaller. So, what it means is that the quadratic terms, that is these terms, are much smaller than the linear terms, regardless of the differentiation. Basically, this resolves the concern that in the continuity equation which was presented here, the linearized, we basically dropped the terms without the consideration of the fact that in the first term here we are differentiating with respect to time t. Well, in these terms we are differentiating with respect to the space x. So, what if the density, acoustic density, were to vary rapidly with distance, but slowly with time? So, now that is the reason that we could probably introduce some non-dimensionalization constant, and which is your given by this set of variables, and what we see immediately that delta rho tau dagger, this is a linear term, and similarly u dagger z is also a linear term, and u dagger and delta rho z dagger, this is clearly a quadratic term, and so is this one. So is this one. So this is the second order term, these two, and the first order. So basically, that's how we retain this, and when we put that back into the dimensionalization constant, we get back the linearized version of continuity equation. So this equation is very important. I would number this as 12, linearized continuity equation. Similarly, let us pull out the momentum equation now. Momentum equation, which is this. So let me write it down. Rho times u t plus u times u x is equal to minus del del x of p by this. We again make an assumption that well, this is not changing with space, and rho naught this is equal to minus this one. So basically what happens now is that if we expand the left hand side out completely, we would get rho naught times ut plus rho naught times u into ux plus rho tilde times ut plus rho tilde times u into ux plus p tilde x is equal to 0. Now clearly let us identify the different orders of term. This is your first order term clearly, and so is your this one, rho naught, and rho naught is the ambient quantity, and you are just differentiating velocity with respect to time t, and here you have your first order quantities, and this term p tilde into ut, this is a second order term. So I am putting two lines underneath it, and so is your the convective term ux into u, which I am also putting double line, and this quantity is actually a triple order quantity. So this can be obviously can be completely ignored. So based on the same arguments that I presented for the continuity equation, what we could do possibly is get rid of the second order terms initially, and then the third order terms as well, ending up with this one, which is nothing but so I am going to call this as equation number 13, right, equation number 13, and this was equation number 12. So now what we need to do is that this relation equation number 11 and substitute that in equation number 12 and 13. That is to say, we will now formally replace all the density variable in terms of the pressure perturbation variable. So let us begin the stuff for the continuity equation, and which basically means is that your continuity equation is equation number 12. So what it means is you have your p tilde is c naught square times rho tilde. So p tilde t is equal to c naught square times rho t, and which means p tilde by c naught square is equal to rho naught t. So this we will put back in the continuity equation, and to basically end up with rho naught times ux equals 0. All right. So this is our equation number say 14, and let us bring out our equation number 13, which is, we do not need to do any simplifications here in terms of substituting for density, we can just use it. Let me write it down again here. You have your rho naught times u del del t of u plus del del p tilde of x is equal to 0, 15. So, we need to now eliminate. So, I would just put it like this. We need to eliminate u and put everything in terms of p. So, what do? We differentiate equation 15, which is actually the same as equation 13. I just replaced it. I probably not want to do that. I would just differentiate this with respect to the space, that is x. To get this is square, and again differentiate this with respect to time t to get, well, say equation, well, still 14, and this would be 15. Subtracting from 14, we get so we end up with our familiar equation. You can also write this as like this, just putting it like this. So, finally, we arrived at the one dimensional wave equation, the hyperbolic equation, and now this is the wave equation, because here you have the with respect to time t, it, like I said, like we discussed in the first couple of lectures, it models or governs the propagation of pulses, decay of pulses or some transient waves, the free waves. It also, if you insist harmonicity, you end up with Helmholtz equation, and then you can get the forced response. So, now suppose p is p x t is p of x into e to the power j omega t, where now you have your complex exponential, that is cos omega t plus j times sin omega t. So, if you do that, what do you end up with? If you put this equation here, you actually end up with a ODE rather than a PDE, ordinary differential equation. You end up with a term called omega by C naught whole square operating upon p, this multiplied with p is equal to 0. So, omega by C, now we are gradually one by one introducing important notations that we will use throughout the course in Muffler acoustics and also in acoustics generally. Omega by C is called the wave number, K naught is the ratio of the angular frequency divided by the sound speed, where K naught has a unit of per meter, because this has unit of per second, this has unit of meter per second, this goes away. So, it has units of per meter, K naught has per unit meter. It is like the spatial frequency, just like f or the frequency is how things vary at a particular point or location with time. Similarly, your K naught tells you, if you freeze time, how does the wave vary in space. It is like the spatial frequency. So, basically this can be written like this plus K naught times p is equal to 0. So, this is the Helmholtz equation. Helmholtz equation, one dimensional. Obviously, for three dimensional things which we will discuss in the next week's lecture, we have additional terms. The complication arises just by inclusion of additional terms. So, right now we just focus on the one dimensional aspect. So, with this, I think we will stop the lecture for this class and resume in the next class, where we will take up the cases for the forced response. We will particularly take up the things that we are going to do for forced response, like a piston excitation. We will talk about different boundary conditions like rigid wall boundary conditions, open end boundary conditions, talk about the general solution in terms of harmonic waves, which is something like, I will just give an idea of what we are heading towards, something like solutions of the form k naught x plus b times e to the power, you can put this is minus, this is plus, times e j omega t. So, we will see we can still have waves that propagate along the positive x direction and the negative x direction, and how they satisfy the Helmholtz equation. These equations are central to Muffler acoustics, at least the plane dimensional test case, plane dimensional frequency propagation, wave propagation, and we will talk about that in the next lecture. So, thanks for attending.